So, good evening, everyone. Let us start today's session. So, can you able to see my screen?
Yes, ma'am.
Okay, thank you. So, we'll see one program using recursion, and here, uh, so what has done is there is two kernel program have been written on global. Okay, so one is called dfun, another one is dkernel. The dfun function is called here in the dkernel. Okay, so then here it is printing some ID value, and ID is greater than 10 and ID is less than 10. Return dfun of ID plus 1. Okay, that function is again called, else return 0. Okay, so this is a recursion. And here in this main program, so what it is called as, and it is called as 1 comma block size comma n. Okay, so here n means this particular function. This is called. Then this invoked. After that, this will be executing, and that time recursively based on the condition. So this defund will be recursively executed. So here CUDA device control you have to use. Okay. So this program is for just simulating how we can write recursion in CUDA. Okay. So you can write any type of recursion here. So I'll share the program in chat. So anybody is there to execute, you execute that program and let me know the results. So the results are printed here. Some ID is printed. So you can try this program. So anybody is trying this? Tag says for the entry function cannot be. So error came up. Everything is correct only here. Character internal and character star. So ID is considered here as character. Having in value and then n equal to. So I'll check it tomorrow and I'll tell if there any changes are there in that particular program. After that, I will upload. Okay, so and the next program is synchronization of threads. Already we have seen sync threads in dot pair-based product. Okay, dot product. So here, so in this kernel program, uh, so what we have done is all the threads have been synchronized. So there is some condition is given. Okay, vector size you have to give. The ID is less than vector size minus 1 and vector of ID plus 1 not equal to ID plus 1. So you can print some message like sync threads does not work. Okay, so if it is out of the bound. Okay, so next is block size is defined and the n is also having the value of block size, that is 1000. And here two series of memory locations have been declared, vector and h vector. So vector is allocated in there in GPU and h vector is allocated there in CPU. And the kernel program is called. Then once the calculation completed, that will be returned back to CPU. Then it is printed. Okay. So this will check whether the threads have been synchronized or not. Okay. So even though we have seen so many programs using sync threads, this is a simple program. So this will help you to whether it is synchronized or not. Okay. So these are some two programs. So you check out whether how we can calculate pi. Okay. So 22 by divided by 7. You can try that program. It is also there. So I'll execute these three programs and along with the output, I'll upload there in the sheet. Okay. So we'll go back to some of the concepts. Okay. While doing the we'll do some other programs after some times. So already we have seen CUDA memory model in so many times. Okay, so here in it is in some other context. So in CUDA memory, the CPU can directly contact with the global memory, constant memory, and the texture memory. Okay, so the global memory is otherwise we can say it is a video memory, and so it is mainly used for communicating data between host and device. And what are the data available in the global memory that will be visible to all the threads in that particular GPU. And latency is very high there if the data is stored in global memory. And for example, it is around 400 to 800 cycles. And the throughput is 200 gigabytes per second. So next is the texture memory. Okay, for streaming data and all, you can use the texture memory. This is a one type of memory available in GPU. So usually the texture memory is read-only memory. The size is 12 KB and the throughput is 800 Gbps. So it is optimized for 2D spatial locality. So in two-dimensional, so you'll be getting spatial locality here. So again, one more memory is available, that is constant memory. That constant memory, which is read-only, the size is again 64 KB. So considering all these memories can be accessed by all the threads. You can see the lines here. So all the thread can access all the three memories. Okay. So here, but here within the block, you are having shared memory that will be accessed by the threads within that block. Okay, so other block threads couldn't access the shared memory of some other block. Okay, so while performing a large amount of data, so you could use any one type of memory. Otherwise, if you want to use some streaming data, you can go with texture memory and all. Okay, so next there is some two types of caches are available. Already you know that caches are there in CPU too, but here in caches which are there in block, it contains L1 cache, and latency is very low in L1 caches. It is a shared memory in the sense within the block all the threads can share that particular memory. So here 64 KB shared memory for per SM. Okay, so here in 64K 16 KB is shared and 48 KB is used as a L1 cache. Okay, so for any SM, if you are having 64 KB memory means in that 64 KB, 48 KB is used for L1, 16 KB is shared, otherwise vice versa. Okay, so latency is very less, the bandwidth is very high. So here L2 cache is also available in GPU. Mostly the size is 768 KB. So it is shared among different SM. Okay, different blocks can or different threads. The threads in different blocks can access the L2 cache, and latency is a little bit high here. Okay, while comparing to L1. Okay. So registers. So register takes very important part here in GPU. So number of registers are 32K. It is unified per SM. So if the register here the registers are unified, so the CPU can directly access the register within the GPU. Both the GPU and CPU can access the register inside the GPU. So if you want to speed up your execution, if your data is very less, that time you can use the registers. Okay, and each and every thread can use 21 registers. Okay, so the register length is based upon the address space of the GPU. So the bandwidth is very high here. So 8 Tbps bandwidth. Okay, for very high speed application and the data is very less, you can go with the registers. Otherwise, you can use L1 cache and L2 cache. So here in GPU, the main thing is the data bus is very wider for transferring data in very fast. Okay, so because of that wider, um, uh, the database can transfer data in very fast. So we can say that is fast database. So also we can parallelly transfer data, and see if you want to improve bandwidth again high, so you can share the data or reuse the data. You can share with the help of shared memory, and otherwise you can reuse the data, you can compress the data, and you can recompute, then store and fetch. Okay, so before storing, all the computation you can perform. After that you store. Okay, for storing and fetching it takes more time, so for that you can perform recomputations. Okay, these are the things that you can remember while doing some real-time applications. Okay, so you know what is the latency? So latency is the time required for input-output operations. So here latency should be minimized. Ideally, if it is 0, then it is okay. and then only the processor should get the data available in no time. In practice, memory IO becomes the bottleneck. Okay, we'll see later how the bottlenecks comes, and most of the times, if the fetching is correct, not correctly happen means uh, the GPU will execute the next thread. Okay, instead of executing the current thread, it go with the next thread and all. And you can reduce the latency with the help of the caches. In CPU, if you could store the data in register, it is very fast. Having the caches L1, L2, L3, L4, and you're having RAM and all. In GPU, you won't have RAM or main memory. So you're having very small amount of L1 and L2 caches. And also you're having many threads to execute parallelly. Okay. So even though it is having some latency, that is overcome with the help of the threads which are executing data parallelly. So and also the latency hiding is also there in GPU with the help of massive multi-threading. Okay, so I already told. So if you are having lot of threads, okay, so 32 threads are used for the warp threads. So using that threads, you can execute single instructions parallelly. Okay. So with the help of this parallelization, automatically it reduces the execution time. So you can hide the latency because of the input output operation. Okay. For loading and fetching operations. See here, the latency hiding, you are having different blocks, and each and every block contains some threads. Okay. So this line shows the latency, and so here what happens is the load latency and the instruction latency is usually usually the load latency and the instruction latency or common latencies you can hide. Okay, so other latencies may be there. Okay, and fetch latency may be there, but load latency and instruction latency or the common latencies you can hide. Okay, so these much times if it takes for load and other instruction, that is not considered as latency. Okay, so this much is alone for latency, and there are different threads are available and different thread stalls are there. Okay, this is a thread stall. Okay, there are 4 thread stalls have been represented here. So these thread stalls helps to reduce the latency. Okay, and usually the threads are in order, and uh, it also tells us the mechanism to hide the latency, run lot of threads, so there is always another thread is ready to execute. Okay, so it is not a problem in GPU, even though it is having some latency, and some already told you the latency load, and that is load the instruction, and load the data and instruction latency. So these things are hidden with the help of parallelizing the threads. Okay. So also the locality. So locality is also very very important in on GPU, and so all the threads in thread block can access the data inside the L1 cache. Okay, each and every block contains one L1 cache that will be accessed by the threads. Okay, if the block is having around 512 threads, means at the maximum it is limited to 512. In the sense, sometimes it may have 1024. So if it is having 512, for example, all the 5 total threads can access the data in the L1 cache. Okay. So in Pascal GPU, it is the size is 64 KB. The L1 cache size is 64 KB. And here also, the 48 KB is used as L1 and 16 KB is used as scratchpad or shared. So otherwise, all else 16 KB L1, 48 KB scratchpad or 32 KB plus 32 KB. So likewise, it may be configured. Okay. So the programmer can help exploit locality in the GPS setting. Another form of spatial locality is very, very critical. We'll see. There are two types of localities are available. One is spatial locality, another one is temporal locality. The spatial locality in the sense, so if you are accessing one data in the um, array, okay, so if the location is added with some constant location, constant k, that would be also be accessed. Okay, that is known as spatial locality. For example, so here in this case, a of I is assigned as 0. Okay, and uh, in the next iteration, what happens? A of 1 is also assigned as 0. Okay, so again, a of 2 is assigned as 0. So we have accessed a of I. Again, the a of I plus 1 is accessed. Again, I have I plus 2 is accessed. I plus 3 is accessed. It goes on like this. That is called spatial locality. So in temporal locality, so if you are accessing a of I, okay, so it would be accessed soon again. Okay, the same location. So a of 0 is there means a of 0 is accessed again. Okay, that is temporal locality. So now you can understood the difference between spatial and temporal locality. And these localities are applicable both in GPU and CPU. Okay, so but mostly it will be used in CPUs. And next is memory collision. Okay, so already we know that what is warp threads. Okay, so it is very much used for accessing data from the access word from the same block of 32 words. Their memory requests are clubbed into one. Okay, so if you want to access some 32 words, okay, so normally in var threads, you are having 32 threads combined together and doing the same operation. And here the memory records are coalesced, because if you are having block of 32 words means all the 32 threads are combined together and clubbed together, and it will be doing the 32. Okay, 32 words, block of 32 words are accessed. Okay. Okay, so if you are not using memory collision, what happened is, so each and every load and store instructions, load or store instruction, so it will require one memory cycle. Okay, so so one word require one memory cycle, another one word require another one memory cycle. Okay, likewise, it requires 32 memory cycles. Okay, so once it is coalesced, it is not a problem. All the 32 words can be accessed by the word threads. Okay, likewise, you can reduce the time required for the execution and all. Okay, and so time is reduced, the memory cycle requirement is reduced, but throughput would be significantly reduced. And so you can use the GPU for only computing the heavy kernels. If it is having lot of computations, then only you go with GPU. So your computation is very less. There is no need of using kernels. Okay. So you can run it with your GPU. Sorry, CPU too. See here. Uh, Okay, already we have seen this. So same block of 32 words have been uh, accessed with the help of var threads. Okay, so you can uh, this can be achieved with the help of regular programs. Okay, so dense matrix operations, you can achieve this. So see here, in this particular, there are some 8 threads are there. Okay, so all the 8 threads are accessing all the 8 location at the same time. Okay, so the first thread is accessing first, and the second is second, third is third, fourth. Likewise, it is called memory collaged. Okay, so that this particular data is combinedly accessed by all the threads at the same time. No problem. Okay, see here, at a particular time, only 3 threads are accessing 3 memory location. So in different places, this is uncoalesced. Okay, this is not coalesced. See here, so all the threads are accessing the memory location. Okay, so sometimes the thread 1 is accessing third one, thread 2 is accessing the first one. So likewise it goes on. But anyhow, all the locations have been accessed at the same time. So we can say it is also memory coalescing. Okay. So now you could understood what is memory coalescing and all. Okay. So for reducing the number of memory cycles required for accessing the data, so you can go with memory coalescing. So I think there is one program is available for memory coalescing. Okay. See here. Um, Here we are having NS 1024, and so we are having one array A. So size is also given, and this size is multiplied by thread IDX. Okay, whatever the size and size. So the chunk size is given as 32. So 32 into 0, 32 into 1, like that, it will be added. And here one for loop is given. So it will be start, and if it is less than start plus chunk size, and it will be incremented, then it is stored in some array. The n value is incremented here. And so here in this kernel launch, while performing kernel launch, what happens is, so the n value is divided by chunk size, and the data passed is the value in the A and the chunk size. Okay. So you have to assign some values for A. And so next, there is no printing statement is given. You have to give the printing statement. So next is you are having the CUDA device synchronize. Okay. So all the that means it will be synchronize the CPU and the GPU. Okay, this is for device synchronize. There is a difference between sync threads and the CUDA device synchronize. It is for synchronizing CPU and GPU, and sync thread is for synchronizing all the threads. Okay, so there's a program for that. Okay, so in memory coalescing, what happened is in both GPU and CPU, it is shown here. Each thread should access consecutive elements of a chunk. Okay, that is called strided, and a chunk should be accessed by consecutive threads. That is coalesced. Okay, in CPU, if some threads have been accessing the consecutive elements, that is called it strided. Okay. So if you have used the array of structures, there is one C concept is available array of structures. So has a better locality. And here in GPU, chunks should be accessed by consecutive threads. Okay, so the chunks are accessed by consecutive, the continuous threads. Okay, so that is called coalesced. Here, if you have used structure of arrays, so it will provide the better performance. Okay, so in CPU, if you want better locality, you go with array of structures. If you go with some structure of array, so it will provide some better performance here. So I'll paste the coalescing program. If anyone wants to try, you try. But you have to include all the remaining statements. Okay. So I have pasted the program. Just try that. Just a minute. I'll come back. So there is another one program is available, multi-file C functions. Okay. So normally while writing C program, from the main function you can include more than one functions from outside. Okay. So apart from header file, so if you have written some functions in some other files, that can also be included here. So likewise also here in this CUDA program, you can also do the same thing. Okay, see here, here in multifile.cu, okay, CUDA file, you're having one kernel. Okay, so in this kernel, you are printing some blockade dates, okay, something. And here globally, you are calling one function, void C function. Okay, so after that, if I've written the CPU part, okay, it assigns value of n. It launches the kernel. So again, sorry. So it is device synchronize. Okay. So it is defined, declared here. So and the C function is called after CUDA device synchronize. Okay. So what is there in the C function is uh, Okay, this is a C function. Some printf statement, that's all. That is available. So if you want to separately write some code, okay, you can write and you can store it using .c extension, and you can call that function within that CPU part too. Okay, so you can do in this way for multi-function. In this way also you can write. Okay. So I won't immediately share all these programs. Once I have executed, after that only I'll upload there in the sheet. So because uh, the problem in my Colab is yet to be solved. Okay. So I have to uh, do something. After that only I can able to execute there in Colab. So already we have seen divergence, thread divergence. What is called thread divergence? Anyone? Anyone know that what is thread divergence? Already we have seen. So the divergence means we are having warp threads. Okay. So 32 threads are combined and we can say that is warp threads. Okay. If any one of the thread is trying to access something else other than the same, you can say that is the divergence. Okay. And here we are having some vector size, same thing. And if id is okay, so if you are having more conditions, that time the divergence happens. Okay, so already we have discussed this one, and so you have to avoid all those divergence. So otherwise, we won't the GPU program won't be executed efficiently. Okay, so already we have discussed this one some 2 or 3 days before. See here, what do you check? Always check is, so you have to check whether memory out of bounds, something else is there. But here, what they have done is, if ID, that is this particular ID value, is while dividing the ID value by 2, if you are getting true value, okay, so then vector of ID is assigned by ID, else vector ID will be assigned with vector size into vector size, okay, some two other operations, okay. So that time you'll be getting the thread divergence, okay. And so here you have to give the float, seal of float. Already you know that. Already we have discussed this one too. And once everything is completed, then return back to CPU, then it is printed. Okay. And we'll move to the next. Okay. So already we have seen here in memory coalescing array of structures, therein CPU for better locality, and in GPU for um, better performance. Okay, in GPU, the chunk of data should be accessed by consecutive threads. If it is accessed by consecutive threads, it is called coalesced, and it has done with the help of array of structures for better performance. Okay. See here, what is array of structure? What is structure of array? Okay, both are explained here, and you know what is a structure. Okay, inside that we are having some structure members in the double B characteristic. So after that we have to we are declaring some arrays. Okay, all nodes of n. Okay, there are n nodes are there, and here structure of array. In structure of array, we are having the structure members. All the structure members are array. Okay, all the structure members are array. And here see that when a thread accessed an attribute of a node, it also accesses other attributes of the same node. Okay, so we will be getting better locality. So in this particular example, all nodes of n, okay, node which is having all nodes of n. So if it is accessing A means, and the next time it will be accessing B, and after that it is accessing C. Okay, so we'll be getting better locality. So one data, next data, next data. Likewise, it is accessing. So here, when a thread accesses an attribute of a node, its neighboring thread accesses the same attribute of the next node. Okay, if it is accessing uh, uh, one attribute, what the neighboring thread will do is accessing the same attribute of the next node. Okay, that is first node, first index, and second node, second index. Likewise, this goes on. Okay, and so if you want the better coalescing, you can use the structure of array, and otherwise for better locality and CPU, you will use the array of structures. Okay, how we can write a structure of array and array of structures. Okay, and see here in kernel struct node AOS star all node AS. Okay, so you can use the you can calculate the ID, and the same way block IDX into block dimension plus thread IDX dot x. Okay, so here all node AS of ID dot A equal to ID all nodes AS ID dot B equal to 0.0, all nodes ID dot C equal to C. Okay, each and everyone is assigned with some other value. Here, 0.A, it is having the ID value, and 0.B, it is assigned to 0.0. 0.C, it is assigned to C. Okay, likewise, you can assign. And structure of array. This is array of structure. This is structure of array. Okay. So in this structure of array, so it is denoted by some pointers. Okay, some dynamic memory location. So and character star C, all node is same. So you see here having int A, double B, and character C. Okay, so that is directly passed here. So you can calculate the ID for all ID. So it is accessing these values. Okay, for all the index, it is accessing all the values. Okay, so just see the difference between how the array of structure and how the structure of array can be written. So you can use both the things to write a program to simulate how the array of structure and how the structure of array can be accessed. So in array of structure, the consecutive memory location, what happens is initially in array of structure, initially the memory location contains one structure. One structure is defined. So after that particular structure, all nodes of AOS, the first element. So in the A will be available, after that double B, after that character C. So next, all nodes A of 0 of 1. Okay, so in that first time A, and after that B, after that C. Okay, so likewise it goes on. Okay, I didn't take any diagram from the internet for specifying. I think you could understood what happens here then array of structure. Okay, so you'll be having some continuous memory location. In that continuous memory location, int A is initially there, after that in double B, after that character C. So next node is after that int A, double B, character C. So likewise it goes on. Okay, that is array of structure. In sorry, what I told is structure of array. Okay. So what I now told is the structure of array. This one. First you are having A, after that B, after that C. And next, what happens in array of structure? Just a minute, I will show that. What is there in array of structure and what is there in structure of array. Okay, see here. This is array of structures. Okay, A0, B0, Z0, D0, E0. After that, A1, B1, C1, D1, E1. Likewise, it goes on. In structure of arrays, you are having A0, A1, A2, etc. And after that, B0, B1, B2, etc. After that, C0, C1, C2, etc. Okay, likewise, it goes on. Okay, so you could see the difference between array of structures and structure of array. This is a difference between both the things. Okay, so here, so that only the area structure can be used there in the CPU, and the structure of array can be used in the GPU. Okay, for one instance, all the variables are sequentially stored in the structure of array. For one structure, one complete structure wise stored in an array of structure. That is the difference. Okay. So you can write the program using structure of array and array of structure. That is also available. And the same code is here there. Okay, you define the structure of array, the array of structures, and same assignment. Okay, same calculation and assign. Okay, so after that you can allocate memory and print everything. Okay, that is there. So I'll execute these programs, and along with the output, I'll update in the sheet. Okay. So in today's class, what we have seen is some memory. So which memory is faster and which memory is slower for different applications. See, if you want the faster memory, you can go with some faster memory. Like some caches are available. L1, L2, L3, L4 caches are there in CPU, but in GPU, we are having only two caches, L1 and L2. Otherwise, we are having some global memory, texture memory, constant memory, all those memories are available. Based on the application, you can choose any memories for our application. So after that, we have seen some memory coalescing, and what about the what threads will do, what happens while performing divergence. Okay, so what divergence is a bigger problem. You have to avoid that divergence while writing the programs. So next we have seen what is the structure of array and array of structures, everything. Okay. So any doubts regarding these concepts? And again, I'm having one more program for matrix multiplication. Okay, so the main thing here is you can calculate time here. The time calculation code is also available here. Okay, so here the RT clock is used, and time zone, time value, those things are used here. Okay, so using that you can print the time in exactly correct manner. Okay, so seconds, hours, minutes, seconds manner. Okay, so all the time related things are here. Then having the seconds, everything is calculated. So I also share this both the documents. You can uh, execute those things. Okay, so anything else? Okay, shall we wind up the session today? Okay, thank you.